In this video, we'll be doing the different kind of decay equations, finding out whether the decay equations are possible by applying conservation of charge, conservation of baryon number or lepton number, and so on. So let's just get started. First, just to recap the different kind of subatomic particles. So the particles are, so if I just go through what we did in the last video, so particles can be categorized into leptons. So leptons are fundamental particles because they cannot be further broken down into other particles. There are 6 kind of leptons, and then you have hadrons, which are made up of quarks, and there are 2 categories of hadrons. So one is baryons and one is mesons. So baryons are the one which is made up of different 3 quarks, and mesons are made up of quark and antiquarks. So baryons would have every single baryon would have a baryon number of +1. So the different examples of baryons we saw in the last class are protons and neutrons, and the example of mesons are pions and kaons. Okay, and every baryon would have a baryon number of +1, whereas if it is an antibaryon like antiproton or antineutron, it would have a baryon number of -1. Mesons would have a baryon number of 0, and even leptons would have a baryon number of 0. Leptons, on the other hand, would have a lepton number of, so I'm just writing the most important one, electron, muon, neutrino. So they will have a lepton number of +1, whereas the antiparticles of electron, which is a positron or antimuon or antineutrino, would have a lepton number of -1. So these are the different subatomic particles. So when you're trying to conserve, to find out whether a given equation, decay equation, is possible or not, we try to conserve the lepton number. This is more in detail. You can pause and go through it. So as you can see, baryons, which is made up of 3 quarks, will always be +1. Antibaryons, 3 antiquarks, -1. Mesons is 1 quark and 1 antiquark, so B is 0. And non-hadronic particle like leptons or photons, baryon number will be 0. Now, the balancing checklist. How do you find out, what do you start with when you start balancing or finding out whether a given decay equation is possible or not? The first thing that you need to do is find out whether the charge on the left hand side is equal to charge on the right hand side or not. Second, conserve the balance. So I'm just going to write it here. Conserve charge. Okay, is the charge conserved or not? Conserved charge on left hand side and right hand side of an equation. So suppose if you have a particle equation, let's say a fundamental particle A is decaying into B and C. So conserve whether the charge of A is equal to the charge of B and C or not. Then conserve baryon number. So this should be conserved. So if you have a +1 on left hand side, so if this is B equals to +1, then they should both have B equals to +1. So this should be conserved. If it's a lepton, conserve lepton number. Okay. Sometimes you might have to add neutrinos or antineutrinos to conserve charge. Sorry, not to conserve charge, to conserve energy or momentum. And also make sure that you use correct particle symbols. Okay, so I'm going to go through different questions to ensure that we understand all of this. So neutrinos or antineutrinos to conserve energy or momentum, to make sure. So suppose if I just write A gives B, so that would not be right, because then momentum and energy will not be conserved. Okay, so here's a checklist. Go ahead, pause and take a read, and then let's just see some examples. So if there's a beta decay of a neutron changing into a proton, so first let's try and complete this, because this is not a complete equation what I've written here. So if a neutron is changing into a proton, which is what happens in a beta minus decay, so obviously on the left hand side the total charge is 0. So to make 0 charge here, so proton has a positive charge, so obviously then electron will be emitted. That's why this is a beta minus decay. Plus, to conserve energy, an anti-neutrino is also emitted. So this is a symbol of anti-neutrino, an electron, which is beta minus decay. Now let's see what is the charge. The charge on the left hand side, this is 0 charge, so I'm just conserving charge. Q is the symbol for charge. So 0 plus 1 minus 1, and this has 0, so total charge on the right hand side is also 0, so charge is conserved. Now neutron is what kind of example? Okay, so just going back, you can remember neutron is an example of a baryon. So baryon is plus 1. Okay, so conserving now baryon number. So here you have plus 1. Proton is also a baryon, so plus 1. Electron is a lepton, so 0. Neutrino is also, antineutrino is also a lepton, so 0. So baryon number is also conserved. So this shows that this particular thing is conserved. Now to see if lepton number exists or not, what do we have for the left hand side? Neutron, there's no lepton number for neutron. Okay, so this is 0. Then proton, no lepton number. Electron has a lepton number of 1, whereas an antineutrino would have a lepton number of -1. So that means this is emitted to conserve the lepton number of this, whereas electron was emitted to conserve the charge of proton. So this and this. So the purple shows charge. So do you see how the decay equation is working? Okay. Right, let's try. Now go ahead and pause and try to do it yourself. So proton changes into a neutron. Obviously the charge is not conserved. So E plus and plus a neutrino. Okay. Now let's see. So first the charge. So charge is plus 1, 0, plus 1 conserved. Okay, then baryon number. For proton, the baryon number is plus 1. Neutron, it is plus 1. Rest lepton and lepton, so 0. Then lepton number is a baryon, so no lepton number. Neutron is also 0. Whereas now positron is an anti-lepton, so -1. So neutron is emitted to conserve the lepton number. All right, so this is also 0. That's it, simple. Now this is how we are interpreting the equations, by trying to read the charge, by trying to read the conservation of charge, baryon number, lepton number, identifying particles, what kind of particles I have to write. Now how did I decide that I have to write a positron there? It is because I have proton, the charge particle that would conserve proton positive charge is a positron, and that's why it's a beta plus decay. And also sometimes some exams questions would ask you to identify what kind of interactions are happening. Okay, so if there is a flavor change of a quark, it's always a weak interaction. Quarks always change flavors by weak interaction. So in the beta minus and the beta plus decay, so I'm just going back. So here, as you can see, there's a change of the quark. So this always happens with a weak interaction. Okay, So we are supposed to know that for some of the questions, whenever it involves charged particles and photons, the interactions are always electromagnetic. And whenever it involves hadrons, it is always a strong interaction. Okay. So just showing you then this. So again, pause and take a read, and let's just do some questions. A sigma plus particle is a baryon. Okay, fine. What is it? Can decay into a positive pi ion and neutrino. Again, as I've told you, always make diagrams or equations when you're just starting about a new particle. A positive pion plus a neutron. Whether the conservation law of charge. So first let's see charge. So what do we have here? +1 and +1. Yes, the charge is conserved. And a baryon number. It is a baryon, right? So the baryon number of this one is +1. And what is a pion is a meson, so that is 0. Neutron is a baryon, that is +1. So the baryon number is conserved. Okay, now to remember this, just try to remember this diagram. A particle, fundamental particles, two categories, leptons and then hadrons. Okay, try to remember this category, and leptons are the fundamental particle. So outside of the nucleus, electron is a fundamental particle, so it's a lepton. And then neutrino is also a fundamental particle, so they will have a lepton number. Whereas hadron, which is a baryon, it will have a baryon number. So this is 1 or +1. Example is proton and neutron. And mesons will have baryon number 0, and examples are pion and kaon. Oops. Okay, so if you try to, every time when I try to put these numbers, this is the diagram I try to remember in my head, and then I solve it. Okay, let's try this one. When a neutron decay, a down quark changes to an up quark. So this equation is already given. Down changes to an up, and an electron is emitted and an anti-neutrino is emitted. Conservation of charge, baryon number, lepton number, that this transformation is permitted. So let's just start with the first one. Conservation of charge, a down quark. So I'm just writing this equation here. U plus E minus plus antineutrino. So this is charge. This is the down quark is a charge of -1/3e. And then up quark is 2/3 e. This is -e. The charge of an electron is 1e. And the charge of neutrino is antineutrino is 0. So this is -1/3e, and this is also -1/3e. So charge is conserved. Done. Now let's see the baryon number. For a down quark, the baryon number is 1/3 e. Okay, if you want to see, go back to the first video and see I've made the table there. And then up quark is also 1/3 e. Electron is a fundamental particle, so no baryon number. Anti-neutrino is also a fundamental particle, so no baryon number. So this is equal lepton number. Now, quarks do not have a lepton number because quarks are hadrons, so 0. Electron have a lepton number of +1, and antineutrino has a lepton number of -1, hence 0, conserved. Okay, so learn as you go, then it would not be that difficult. Okay, so if you are missing out on anything, again pause and rewind and do it. All right, let's go ahead, pause and try to do it yourself. Which conservation laws would be broken by this reaction? I think it is pretty straightforward. I don't need to do anything else. The charge itself, +1, 0, plus 1 minus 1. So charge is not conserved. This is 1 equals to 0, so that's not possible. So charge is, so the state, charge is not conserved. Why? This explanation. So this is the explanation. The state part is charge. And this is the explanation part. I've explained is why it's not conserved. One conservation law that would not be broken in this equation. Okay, fine. Let's try with the lepton number first. Okay, I'm writing this equation here. Plus n gives p plus pion. So pion, obviously, because they are mesons, the lepton number is 0. Neutron, again, a hadron, which is a baryon, so lepton number is 0, 0, and 0. So lepton number is conserved. Okay, we can try and conserve, see if baryon number conserves or not. Halak is asking only one, so we're not interested in the second one, we're just doing it for the second one. So this one is then pi, baryon number is pion, yeah. So the baryon number for a pion is 0, it's a meson, and then neutron is 1, proton is 1, and again it is 0. So baryon number is also conserved, not broken. Right, let's do this one. A delta particle, so delta is written like this, decays into a proton plus a pion. Okay. Alright, so this one has to be a negative pion. The reason is my proton is a positively charged and they both are going in the opposite direction. So if this is positive, this is negative. Now, how do they move in the opposite direction? Is because all the particles are under the effect of magnetic field. If they end up making two different curves, it is because it have two opposite charges. So why it can be concluded from the diagram that delta is a neutral particle, it is because the tracks present are opposite in curvatures. Now let's do the second part. Deduce a charge on the pion. So obviously the charge on the pion, because they're opposite curvature and the charge has to conserve, the proton is positive, so the charge on the pion is negative. Complete the particle. Okay, I've done that, but you can just try and do that again. Now we can include the charges plus pi negative. Why the delta particle must be classified as baryon based on the evidence of the decay. Now this one was the baryon number 0, was the baryon number of this one plus 1, so the baryon number of this one has to be a plus 1, so this delta particle has to be a baryon to conserve the baryon number. So I'm just writing to conserve the baryon number. How the momentum of the proton compares with the momentum of the pion. As you can see, whose radius do you think is large? The radius of the proton is large. Okay, let's just go back. So as you can see, this one is curving more than proton, so the radius of the proton is larger. Okay, so the radius of proton is larger than the radius of pion. Now, if the radius is larger, say now if we remember from the magnetic field video, your radius is momentum over BQ. Or I'm writing BQV is mv square over r. Yep, okay. So yep, that's right. So if I see the radius of proton is higher than the radius of pion, so obviously the momentum of proton has to be higher than the proton momentum of pion. You can write this in your words. Okay, let's do the next one. the neutral lambda particle is a baryon. Fine, we've discovered that. A student suggests 5 ways a delta particle might decay. These are this suggests which of these is not possible. All right, let's try one by one. Let's try the first one. So the delta 0 is proton plus a pion, which we have seen in the previous question that this is very much possible, isn't it? So this is possible. Let's just see the next one. Why is this possible? Because the charge is conserved, the baryon number is conserved. So this is definitely possible. Now let's do the next one. Delta 0, what's the next one? Delta 0 is E positron plus electron. So delta 0 is, positron plus electron. So the charge is conserved. Both sides it has 0 charge, E plus and E minus. But the baryon number, so this one has a baryon number of 1. Whereas on this side, electron has a baryon number of 0. Positron has a baryon number of 0 and electron also has a baryon number of 0. So baryon number not conserved, hence the second one is not possible. Let's try the third one. What's the third one? Delta is changed into neutron and a pion. So delta 0 is changed into a neutron plus a neutral pion. So obviously now this is the baryon number. Let's try plus 1. Neutron has a baryon number of plus 1. So this looks like this is possible. Charge is conserved and baryon number is also conserved. Next, the third one. So this is possible. The first one is possible. This is not possible. This is possible. Let's do this one. So the fourth is not possible because then energy and momentum is not conserved. One particle cannot change into another particle of different mass because then the momentum will not be conserved. Okay, so the one particle decay is generally not possible. A heavier particle cannot decay into a lighter particle, momentum cannot be conserved. Then this last one is delta changing into delta 0 changing into proton plus what is it? Pi. Okay, so it's clearly not conserved. What is not conserved is the charge is not conserved. Okay, so the charge is not conserved, hence not possible. So only 2 are possible. Okay, so this one is not possible. So only 2 are possible here. All right, so that's it. So this is a fairly easy topic. Only thing is that we struggle in this topic is because we forget to link each of the particle to the respective numbers and forget the name of the particles. So particles is leptons and hadrons. Leptons are fundamental, hadrons are further broken into baryons or mesons. Baryons because of the 3 different quarks, meson is 1 quark and 1 antiquark. Every baryon will have a baryon number, lepton would have a lepton number. Right, so that's it. Thank you for learning. Well done and keep learning.